Okay, so this is our second lesson in our unit on probability and statistics. And if you are watching this video in the 2020-2021 school year and we're doing the flipped classroom, this is going to take you about halfway through the next chunk of notes. You will not need to upload the notes into Focus until after I have assigned and you have watched the second video. So you will not upload the notes after watching this video. You're going to hang on to them. We're going to do some stuff in class, and then you're going to watch the next video, and then you will upload the notes. And that's for the 2020-2021 school year. So the first thing that you see in your notes, it says discussion of the warm-up. And this kind of harkens back to a few years ago when I did the notes, and we would begin every class with a warm-up, and just everything was structured differently than it is in the current school year, when I'm recording this. And in that warm-up, we looked at two situations. One, you can see here, it says the outcome of rolling a die and the effect of the outcome of a spinner. So if you were to roll a die and then spin a spinner, would the spin on the spinner be influenced by the outcome on the die? And they wouldn't. So if you picture that situation for a moment, like you're rolling a die and then you're spinning a spinner, the two events have nothing to do with each other. And the probability of the spinner doing something is in no way impacted by whatever happens on the die. And that is an example of something called an independent event. Now, the second situation was an example of something called dependent event. So if you look at the writing on your outline, the card chosen first affects which cards are left and then therefore influence the second drawing. So that situation was you have a deck of cards, you draw a card from the deck, and there's a certain probability for whatever that event might be. Like what's the probability of drawing a red card or a diamond or a face card? Now you keep that card, you don't put it back in the deck, and now you draw the second card. Now the probability is different because of the card you kept. So if you follow the reasoning there, it says, so what are you doing? The card chosen first, whatever that card is, affects which cards are left and therefore will influence the second drawing. So if you drew a king on the first draw and you kept that king, now the probability of drawing a king is less likely than like it was before for the first drawing. So what that's getting into is the idea of having multiple events, okay, where you have more than one thing happening and whether those events influence each other. So you have an event that happens first and then you have an event that happens second. And does the outcome of the first event affect the probability of the second event? So here are some examples of independent events so you can get an idea of what kinds of things are independent. And I have in my notes, today's temperature, okay, which the day that I'm recording this, I think the high today is 58 and I think it's like 40 something outside. It's been recently a lot warmer than that, but today is kind of chilly. And the cafeteria lunch. Okay, there's a menu for what they're going to serve in the cafeteria. And it has absolutely nothing to do with the temperature today. So whether it's likely that we're going to have a warm day or a cool day, that has nothing to do with whether they're serving pizza today. Another example of independent events might be your hair color and your favorite TV show. Okay, they're unrelated. So if we were to look at the class and I would say, what is the probability that I pick somebody at random and they have black hair? There's a certain probability for that. And then I think the second event is, what is the probability if I draw someone at random that they are a fan of anime? That those two probabilities don't impact each other at all. So somebody with black hair is equally likely to like or not like anime as somebody else. And so those would be independent events. Examples of dependent events, these are things that would influence each other, would be maybe today's temperature and the jacket that you wear. We'll just say, and your jacket. Okay? Because if it is 65 degrees in the morning when we're all arriving at school, it's a lot less likely that we're going to be wearing a heavy kind of coat. If it is 40 degrees outside, it's more likely. Now, there's always those people that wear big heavy coats even when it's warmer, and those are the people that show up in t-shirts even when it's cold. But this has to do with probability, likelihood. If we were to watch everybody this year in the temperature check line, to come in there, and we were to pick people at random, if it's only 40 degrees out in the morning, the probability that we're going to pick somebody who's wearing some kind of coat is much, much higher than if the early morning temp is, 70 degrees. We would be less likely to pick somebody who's wearing a coat. So you get the idea of they're dependent. And then because I'm a runner and I can't help but put running examples into things, I have the amount of training that you put in to preparing for your target race and how you feel on race day. And again, it's not that like if you train perfectly, you're going to have this awesome race all the time. That doesn't happen. Sometimes you can put in all the training, do everything right, and you wake up with a head cold on the day of the race. Or it's pouring rain on the day of the race, or it's blazing hot, and you end up not feeling great on race day anyway. And then there's those like lucky people who just don't train and then they go out and have an awesome race. We're talking about the likelihood of feeling good on race day, given that, or as related to the probability that you've trained well. And every year for Marathon High, we get a group of students and we train for a half marathon. And some of those students feel amazing on race day and some of those students don't. And to a large extent, it has to do with how well they trained, how closely they followed the program they were supposed to be following. All right, now caution here. Some examples may be ambiguous. This really gets into stuff that's not clear cut. It's not black and white. Ambiguous means kind of unclear. So this means you could argue either way. For instance, your grade in math and your grade in Spanish could be seen as dependent or independent based on the individual. And so there's just a lot of factors involved. So for instance, some people could argue that you're hardwired to be good at certain things. And some people have an aptitude for languages. They just pick up languages very quickly. Some people have a very clear-cut aptitude for math. It just makes sense to them. And so you could say, well, those are independent from each other. I have an aptitude for math. It just clicks. It just makes sense. It's logical. But man, I struggle with pronouncing, rolling my R's in the middle of a word. Or vice versa, that you just pick up languages, that, especially if you already speak more than one language, sometimes picking up an additional language is that much easier. Your brain has just developed to be able to communicate. And math, looks like alphabet soup on the page. Now, you could argue, though, that they are actually dependent, because the same discipline and study skills that make you successful in math will make you successful in Spanish. If you are a student that keeps track of your assignments, that budgets your time in the afternoon to make sure that you're getting your work done, if you're proactive when you're going to be absent, those are things that carry across all of your classes and will improve your grade in all of your classes. And if you are the kind of student that loses track of your assignments, that you're always playing catch up, well, playing catch up in math is just as bad for your grade as playing catch up in Spanish. It just actually doesn't work very well. And so here's the deal. Try not to overthink the situations. Try not to nitpick them and pull them apart. Ask for clarification when you need it. Whatever you decide, try your best to explain your reasoning for how you arrived at the conclusion for whether they're independent or dependent. So that brings us to one of my favorite vocab words, which is mutually exclusive events. So this is actually really good. If you think about mutually, okay, let's kind of pull apart the words here. Mutually, I'll use it in a totally different context and see if you can connect the words. If you and your boyfriend or girlfriend break up and you say the decision was mutual, what that means is that the decision was agreed upon by both sides. Okay, so both you and your boyfriend or girlfriend, you both agreed that it was best for you to break up. You say this was a mutual decision. Exclusive means to exclude something. And so mutually exclusive events are events that cannot happen at the same time. They exclude each other by virtue of what they are. And so and one, like the first event excludes the second event excludes the first event. It means it happens on both sides. So you get an idea. What would be some mutually exclusive events? Being in room 506 and being in room 602. Okay, it is impossible for both of those events to happen at the same time. If you are in room 506, it is completely impossible for you to also be in room 602. If you are in room 602, it is completely impossible for you to be in room 506. Okay, it's not possible. And one of my favorite examples is this, and students always like to argue with me on it, but I'm right. And this would be talking and listening. Okay? If your mouth is engaged, if you are busy, if your brain is busy forming words and forming that thought and getting that thought out, your brain cannot also be busy intaking and processing information that's coming in from the outside. Notice I didn't say talking and hearing. You can hear if somebody is, like if there's noise coming from someone's mouth, but you can't actually listen and process what they're saying if your own mouth is going. And it can also be true for like texting. If you are texting, you can't give your attention to what someone is saying, which is why texting in class is so destructive to being able to learn, because your brain can only process and concentrate on so many things. Some people will say they can multitask, but the truth with multitasking is that usually the quality of whatever you're doing suffers. And if somebody does multitask well, one of the tasks that they're doing does not require their attention. It's something that they can do without paying a lot of attention to it. Okay, so let's take a look at the probability aspect of this. So here's an illustration. You have 3 shirts, a red shirt, a green shirt, a yellow shirt, and 2 pairs of jeans, blue and black. If you choose a shirt and a pair of jeans at random, what is the probability that you will wear the red shirt with the black jeans? And I'm going to kind of circle this word right here. With means and. Okay, so you're wearing the red shirt and the black jeans, both of them together. So, and the black jeans. So what we're going to do is actually list all of the possible combinations, and then that will enable us to get the probability. So I'm going to use some shorthand here and some abbreviations. So we're going to have the red shirt with the blue jeans, and I'm going to use BU for blue. You could have the red shirt with the black jeans, and we'll use BK for black. You could have the green shirt. Oh, wait a minute. There we go. With the blue jeans. You could have the green shirt with the black jeans, and you could have the yellow shirt with the blue jeans and the yellow shirt with the black jeans. Now notice when I listed all the combinations, I didn't just randomly throw stuff out there. I didn't say, oh, red shirt, blue jeans, green shirt, black jeans, yellow shirt. That what I did was I picked a color of the shirt, and then I went through all the pairs of jeans, and then I cycled to the next color of the shirt and held the color of the shirt stable while I went through all the jeans. So if you have 3 shirts and 2 pairs of jeans, what you have is 6 possible outfits. So what is the probability that you will end up wearing the red shirt with the black jeans? Well, there's the red shirt with the black jeans. So the probability of choosing the red-black combination is 1 out of the 6 possible outfits that you have, or expressing that as that ratio, it would be 1/6. So the probability that you will end up wearing the red and the black combination is 1/6. In an example like this, it is easy to list all of the combinations. Okay, because we're not dealing with tons and tons of combinations here. But what if, and I don't know why I did it this way, 7 shirts and 20 pairs of jeans. I think it's more realistic that you would have 20 shirts and 7 pairs of jeans. I don't know who's got 20 pairs of jeans, not me. But anyway, what if we had 7 shirts and 20 pairs of jeans? We would not want to list them then, because there would just be way too many possible outfits to list. In that case, we would use a formula to help us figure it out. And here's the formula. The probability of A and B is equal to the probability of A times the probability of B. So in this particular example, okay, what this would be is the probability of red and black. Okay, that both of them happen is equal to the probability of the red jeans, a red shirt, times the probability of the black jeans. Okay, so that's how that formula would apply in this particular case. All right, so let's confirm this using the example above. So looking at the shirts, remember that we had 3 shirts. So we have red, green, and yellow. So the probability that you're going to pick a red shirt was 1 out of 3. There were 2 pairs of jeans, the blue and the black. So the probability that you would be pulling the black jeans is 1 out of 2. So the probability of red and black is going to be the probability of red, which is 1/3, times the probability of the black. Now, just as a quick review with your fractions, multiplying fractions is the absolute easiest thing on the planet to do. You multiply straight across the top and straight across the bottom. You do not need a common denominator. It's the easiest thing to do. So I don't want you to freak about it. So going across the top, we have 1 times 1 is 1. And 3 times 2 is 6. And so the probability of wearing red and black is 1/6, which matches the answer that we got over here from listing all of the combinations. So if you have bigger numbers, for example, and you don't want to list all of them, you would resort to using the formula instead. So let's go back to the 7 shirts and the 20 pairs of jeans. Assuming that only one of those shirts is red and only one of the pair of jeans is black, that's kind of ridiculous. It's hard to believe that you could have 20 pairs of jeans and only one of them is black, but it's this math class, so why do we care if it's realistic or not? So let's kind of think this through. The probability of choosing a red shirt in this case would be 1 out of 7. The probability of choosing the black jeans would be 1 out of 20. Now, if you did happen to have more than 1 pair of black jeans, it would just change the probability there. So maybe you have 4 of those jeans are black, and so the probability would be 4 out of 20, and it wouldn't actually change anything about how you would do this problem. It's pretty good news. So the probability that of wearing the red and the black in this case would be 1/7 times 1/20th, and we just multiply straight across. 1 times 1 is 1, 7 times 20. Now the easiest way to do that is to do 7 times 2, which is 14, and then you have the extra 10, which makes it 140. So the probability in that case that you would choose the red and black combination is 1 out of 140. So here's the question. What is the probability of A and B both happening if A and B are mutually exclusive? So take a moment while you're watching this and think about it. Let's go back to the definition of mutually exclusive. Right here. Mutually exclusive events are events that cannot happen at the same time. So what is the probability of A and B both happening if A and B are mutually exclusive? Hopefully the answer that you're thinking of is 0. There is 0 chance that you will be in room 506 and also room 602. Okay, 0 chance that both of those could happen. All right, so that is the first part of the lesson on probability of multiple events. Again, if you are my student and you are watching this in the 2020-2021 school year, you should have filled out the notes up to where, as far as we've got. And we will do some work in class on probabilities involving and then the next video that you will watch will cover the rest of your notes and the rest of the outline. When you're done with that, you will upload the notes into Focus. And that is only for the 2020-2021 school year, unless I've told you otherwise.